session on fundamentals of electrical engineering as a part of the NPTEL course number NOC 22113. So today is the week 0, so I'll be discussing a few of the questions that is there in the week 0 assignment. So let's begin. In case you have any questions, you may ask in the chat box or unmute and speak up. So I hope you guys are all going through the week 1 lecture. So we will be solving a few problems based on the week 1 lecture from the next class. For this class, it's just a demo class where we are going to solve a few of the problems of related to the fundamentals of electrical engineering. The first question is, let's say the resistance of a wire of length L and diameter D is 4 ohm. If the length is increased by 100% and the diameter is reduced by 50%, the new resistance of the wire will be, the four options are given. You have to choose which is the correct answer. So I hope everyone can hear me and see the Jamboard clearly. Okay. Okay, so let's start solving this. So um, we know resistance of the wire is given as rho L by A. Here rho is the resistivity, L is the length of the wire, and A is the area of cross section. Now area is equal to pi r square, right? The area of cross section of the wire. This area of cross section. Now the diameter is given and the length is given and the resistance of the wire is given. Now a new dimension is given. You have to find what is the new resistance. So for the first one, resistance is given as 4 ohm. Since resistivity is not given, we'll keep it as rho. Length is L and area of cross section is pi. Now instead of radius, the diameter is given. So radius is actually half of the diameter. So d by 2 whole square, right? So we get, like, if we just put this denominator into the numerator, it is 4, right? 4 rho L by pi d square. Now for the second case, since the length is increased by 100%, that is, it goes from L to 2L, and the diameter, it reduces by 50%. So diameter goes from D to D by 2. So the new resistance will be rho L by, it will be 2L in place of L, and area is pi d square, so it will be pi d by 4 whole square. Reason is radius is half of diameter. Since diameter has decreased by 50%, so it will be d by 2 by 2, that is d square by d by 4 whole square. So if I write it properly, let's take this 4 square is 16. If we take it up and multiply with 2, we will get 32 L by pi d square. Now from here, if we just calculate the value of uh, rho L by pi d square, it will be, this 4 and 4 will cancel, so we will get 1. So if we simply put this value 32 into the rest rho L by pi d square, we get it from this equation. So it is into 1. So 32. So the correct option here will be option D, 32. So let's go to the, I hope everyone has understood this. The next question is, the power delivered by a 2 ampere DC current source if it is in short circuit, and the power delivered by a 5 volt DC voltage source if it is open circuit, or respectively. The four options are given. So could you try this out? So right now we will dive into the solution since there are no participants. Um, So power is given by I square R, or it can be given by, if voltage is given, um, so like in the first case, the current 2 ampere DC current source is mentioned, and it is mentioned short circuited. So it will be like there is a current source and there is short circuit. The output terminals are short circuited. So since it is short circuited, the resistance will be equal to 0. So power will be 0. Since I square R, since R is 0, so power will be 0. Now in case of voltage source, it is given, it is open circuited. So power is given by V square by R. Now since like the circuit is open circuited, so the resistance will be equal to infinity, right? So it will be V square by infinity. Now inverse of infinity is 0. So the correct option will be C. In both the cases, the power delivered are 0 and 0. I hope everyone got it. Now we will move to the next question, which is given for the network. We have to take out the time constant. Now time constant is given by RC, since it is a RC circuit. Now equivalent of this resistance and this resistance, since they are connected in parallel, this point and this point are same, so they are connected in parallel. So the net resistance, let's call it R dash, will be 1 upon R1 and R2. R2 here is 2R. So it will be basically 3 by 2, 1 by R. So R dash will be equal to 2 by 3 R. Now in case of capacitance, when two capacitance are connected in parallel, you know they add up. So C will be equal to C dash, let's call it C dash, will be equal to C plus 2C. That is 3C. So now if we consider the time constant of the circuit, it will be R dash C dash. So it will be 2 by 3 R times 3C. This 3 gets cancelled, it is 2 RC. So the correct answer to this question will be 2RC. Right? Now we look into the the fourth problem, where initially a discharged capacitor of 1 microfarad capacitance is fully charged from a 2-volt battery. Now then the battery is disconnected and the same capacitor is connected across a 2 ohm resistor. Find out the total amount of energy dissipated in the resistor at t up to t equal to infinity. That means after a long time. That is all the capacitor will get fully discharged and it will be dissipated in the resistor. So energy that is for now stored in the plates of the capacitor will be E equal to half CV square, right? Now C is given as 1 microfarad and voltage is given as, the battery voltage is 2 volt. So if we calculate it, it will be half into 1 into 2 square. Now this will be in microjoule because the capacitance is 1 microfarad. So it will be 10 to the power minus 6. We can write it directly as microjoule. So if we calculate this, it is 2 microjoule. Now since the time is at time equal to infinity, so the entire capacitor has discharged into through the 2 ohm resistor, and hence the answer will be like this entire energy gets dissipated. So it will be B, option B, 2. Now let's look into the fifth question. So in a series RLC circuit, resistance is given, reactance is given, and capacitance is given, and the frequency of the supply is given. If the circuit is connected across this voltage, the RMS value of the current will be. Now since they are connected in series, the current across all the three elements will be same, right? So this is given as 10 ohm, this is 15 ohm, and this is 5 ohm, right? And the voltage source is given here. So now if you are to calculate the RMS current, current is basically what? Current is voltage by the total Z. Now Z will be equal to the resistance, that is 5 ohm, the reactance, which is given by 10J, and the capacitance. So if we were to calculate this, it becomes 5 minus 5J. So basically the mod value of Z will be square root of 5 square plus 5 square, that is 5 root 2. Now the voltage source is given here. So this 100 is the value of V0, right? So V RMS, since the average of sine square is 1 by root 2, so it will be hundreds. V RMS will be V0 square by 2. So it is 100 by root 2. Now the current will be then 100 by root 2 into 5 into root 2. So it will be 100 by 10, that is equal to 10 ampere, which is given in option C, right? If you have any doubt, you can ask by unmuting yourself, or you can simply type it in the chat box, right? Let me see. Okay. I'm sorry. There was probably a technical glitch. So if anyone has any doubt or could not see through it, let me know. Then we will move to the sixth question, which is a, a 24 ohm resistor and an inductor with reactance 120 ohm and a capacitor with reactance 120 ohm are in series across a voltage supply which is 60 RMS, which has a value of 60 RMS, and the frequency is 50 Hertz. It's a single phase AC source. The voltage magnitude across the inductor. We have to find the voltage magnitude across the inductor. So there is a resistance, there is a reactance, and there is a capacitance. We have to find VL. Since they are in series, the current across all the three elements will be same. So uh, if you find out the voltage, we can calculate the if you can calculate the current, we can calculate the calculate the voltage across this reactance, right? So the total net Z, since so it will be 24, since the inductor and capacitor, the reactance and the capacitance are of the same value, they will cancel each other out. So it will be in resonance, right? So if we have to calculate the IRMS value, it will be um, 60 sorry 60 by 24. um, so now if you are to calculate the voltage magnitude across the inductor, it will be VL. We can give by, since the reactance is given, we can calculate 60 by 24 into 120. So if we cancel, it is 230, it will be 300. So it will be 300 volt across the inductance. Now if anyone has any question, you let me know. Otherwise, um, we will move to the next question. So for the question number 7, the circuit shown in the figure given below is in steady state when the switch is closed at t equal to 0. Assuming that the inductance is ideal, the current through the switch and the inductor at t equal to 0 plus, that is just after closing. So at steady state, what happens is inductor behaves as a short circuit. So if the inductor behaves as a short circuit, like this will be almost no resistance, and the current flowing through here will be 10 by this is 10 volt by 10 ohm. So it will be 1 ampere. Um, now like so as soon as the switch is closed, what happens is in an inductor, the current across the inductor do not change instantaneously. It changes only after a small fraction of time has passed. So as soon as the switch has been closed, all the current have been passing through the inductor. So through the switch, as the question is asked, through the switch the current will be 0. So the current through the switch will be 0 and the current through the inductor will continue to flow at that fraction of time when t equal to 0 plus, that is the switch has just been closed. So the option will be option A. Now for the eighth question, in a circuit, there are 5 nodes and 10 branches. The number of independent KCL nodal equations and the independent KVL equations can respectively be written are given here. Now, when we write the nodal equations, that is KCL, that is if this is a node and by Kirchhoff's law, if this is I1, this is I2 and this is I3, since they are all coming out of the nodes, I1 plus I2 plus I3 will be equal to 0. So if there are other nodes into the circuit, then the total number of equations like this that can be formed is given by n minus 1, that is the total number of nodes minus 1. So since there are 5 nodes, so 4 is the correct answer. Now let's look into the KVL loops. In case of KVL loops, suppose sorry. So in case of KVL loops, suppose this is a voltage connected across a resistor with current I. KVL is written in the form, suppose this is V, so V minus I into, let's call this R, equal to 0. So this is one loop. So in case of KVL, the total number of this kind of equations that can be formed are given by the total number of circuit branches or elements that are present minus the total number of nodes plus 1. So in this case, since there are 10 branches, so it is 10 minus 5 nodes plus 1, that is equal to 6. So the correct answer is option B, 4 and 6. 4 KCL equations and 6 KVL equations can be written. Okay, now let's look into the ninth problem, where two incandescent light bulbs of rating 230 volt 40 watt and 230 volt 60 watt are connected in series across the mains 230 volt. So we have to choose which of the bulb glows brighter, or if they glow with the same brightness. Now, if we consider this bulb, which has a rating of 230 volt and 40 watt, please note that the supply voltage is 230 volt. It is very different. This is just the rating of the bulb. It can be of of different voltage, but like the limiting one should be the supply voltage. Anyway, this now if we are to look into this two individual bulbs, let's call this is bulb 1 and this is bulb 2. So for the 40 watt bulb, the resistance the resistance of this 40 watt bulb will be much higher than that of the 60 watt bulb, right? Because um the power rating of the bulb is given by V square by R. Now, if P is smaller, that means since the V for both the bulbs is same, the R will be higher. So resistance across the 40 watt bulb will be greater than resistance across the 60 watt bulb, right? Now, since they are connected in series, so both the bulb through both the bulbs same current will be passed. So to determine which of the bulb is glowing brighter, we can calculate I square into R. Since the luminescence of the brightness of the bulb will directly depend on the power that is being output, right? This power output can be given by I square R. Now, since I will be constant in both the cases, since like the now the power of the 40 watt bulb will be greater because the resistance of the 40 watt bulb is more, and in both the cases I square is same. So the power of 40 watt bulb will be greater than the power output of the 60 watt bulb when they are connected across the voltage supply of 230 volt. So the 40 watt bulb will grow brighter, and option B is the correct one. I hope everyone has understood this. If not, you can type it in the chat box or unmute and speak. Okay. If not, we will move to the 10th question. Consider an RLC series circuit connected across a AC voltage source V. If the supply frequency of the AC circuit is more than the resonant frequency, then the circuit voltage V is, we have to calculate. So in case of RLC series circuit, if the supply frequency of the AC circuit is more than the resonant frequency, that means the since in case of RLC circuit, like if the supply frequency is equal to the resonant frequency, that means resistance equal to reactance, right? But in when supply frequency supply frequency is greater than the resonant frequency, let's call it resonant frequency as FR, then it is kind of an inductive circuit, that is XL is greater than XC. When the reverse is the case, then the capacitive reactance is more. But in our case, since the supply voltage is more than the resonant frequency, it is kind of acting as an inductive circuit. Now, in case of inductive circuit, you have read, I hope you have gone through the lectures, where the current leads the voltage. The voltage leads the current in case of inductive circuit. So, in this case, option B will be the correct answer because the voltage is leading the current, right? If anyone has any question, you can ask. Otherwise, we move to the 11th problem. By keeping the supply voltage to the primary of a transformer constant, if the frequency is decreased, what can happen to the magnetizing current and the core loss current? Okay, let's look into initially the magnetizing current. Okay, now this magnetizing current is equal to the voltage and the magnetic reactance. It is the reactance, right? So now reactance is dependent on the frequency as 2 pi f into L, where L is the inductance, right? So Xm is directly proportional to frequency, and hence the magnetizing current is inversely proportional to the frequency. So it is given that frequency decreases. If frequency decreases, magnetizing current should increase. So magnetizing current should increase, right? It could be either this or this. Now let's look into the core loss. So I'll just open another slide for the core loss. Now core loss can be the loss from the eddy current or from the hysteresis loss, right? So for the eddy current loss, um, the eddy current loss, the equation is, here K is the coefficient of eddy current, then this is the magnetic flux, then this is the supply, like the frequency, then, and this is the thickness V, right? Now we know that Bm can be written as volume, sorry, volume, this is the volume of the material, and it will be written by volume by frequency. So if we replace this, it is K Bm square in frequency, let it be, sorry, in case of B we are going to replace it, right? So it is V square by F square. The rest of the term remains constant. This F square will get cancelled and it is K V square T into V. So eddy current loss becomes independent of frequency. Now in case of hysteresis loss, let's see. This is a coefficient constant, don't worry about it. It depends on the magnetic flux as 1.6 times, and then frequency and volume of the material with which the transformer is made, this volume. Now if we are to replace the magnetic field with V by F, it becomes V 1.6 by F 1.6, right? And F into V. So typically it is V to the power 2.6 by F to the power 0.6. Sorry, I think I missed. Yeah, no, it's fine. So this hysteresis loss is inversely proportional to the frequency, right? So of course, if the frequency decreases, the hysteresis loss will increase. Now let's go back to the question. Um, so basically here the magnetizing current was increasing, and so does the core loss. Among the core loss, the hysteresis loss was increasing. The eddy current loss was constant. So the answer will be option C. So now this is the last question. So if the direction of the rotation of a separately excited DC motor can be reversed, so option 1 is given by reversing the polarity of the terminal, by reversing the connection of the field terminals, by reversing both the polarity of the terminal voltage and the connection of the field terminals at the same time. Now, which is correct? So this is kind of a, and this is the armature winding and this is the field winding, and it is like just showing the separately excited DC motor. As we can see from this figure, by reversing the field, the direction or direction of this arm, like the motor changes, because either if we change the um, the direction of the armature current or the field current, the direction of rotation will change because the magnetic field is constant. If we change the current direction, what happens by uh, by the Fleming's right hand rule, the force has to change because they has to be mutually the three of them has to be mutually perpendicular to each other. So by by either reversing the polarity of the terminal, the direction of rotation can be changed. Also, if we change the connection of the field terminals, the direction of rotation will change, but not at the same time. So the option will be D, either one or two. So this brings us to the end of our short discussions. If you have any questions, you let me know. Otherwise, we can end the session. So let me go to. So from the next sessions, uh, all the will have live interaction where all the participants will be present, and you can unmute and ask or type in the chat box. This was just a demo session to see if there are mitigate any technical glitches or anything if it happens. So I thank you all, and let's end the session now.